Hey everybody, this is Larry. This is it's just June 3rd here in New York City. I am trying to find a problem that I have not done yet. And today, yeah, I guess I'll do this one. I've been doing them down the line. Maybe I could do a hard one of these days, especially a day that I have energy. But yeah, whatever. Let's just do this one. Go down the list. Today we have 3073, maximum increasing triplet value. Given an array nums, return the maximum value of a triplet where ijk such that they're in order, and they are also in order, both in index and number. The value of a triplet is going to be, this funky thing. Nums of I minus nums of j plus nums of k. Okay. Let's think about this for a second. Well, let's look at the constraint for a second. So n is equal to 10 to the fifth, so we have to do something a little bit smarter than, well, obviously the really obvious solution would be n cubed, but of course that is too slow. But in this case, even n squared is too slow, so we have to try and figure out a little bit, well, just a little bit better. I'm going to drink on this while I give it some think. All right. All right. So given this problem, we have two things, or three choices, right? Given that n is so big, we really only we're limited by at worst n log n. And given that kind of constraint, that means that we can iterate only through one number at a time, and the number that maybe anyway. I mean, there are some other things, but this is my first idea to play around with the problem. I don't know the solution right now. And the choice is going to be ij or k, obviously, maybe. Okay. So let's see, right? So we're trying to maximize this thing, right? So how do we maximize this thing? That means that we want to minimize the middle number, right? We want to minimize the middle number, and then after we minimize the middle number, then we can have the max on the left and max to the right. And I think that actually is enough for me, right? Because that means that here what we want to do is iterate on j. We just brute force. Ideally we want to minimize the j, but it doesn't even matter because as long as we have a j, then we can just add the largest number to the left of the j and add the biggest number to the right of the j, right? And that's pretty much the idea. And of course we can pre-process this at least on one side, because on the other side you can just do it concurrently. But we'll actually do it the lazy way, which is to say we use code and get prefix max or something like this, right? So you give in a nums, which is not the same as this nums, I guess, right? And then you have a prefix array, all positive values. Okay, so I mean the positive value don't change shouldn't change anything. It just sets the sentinel value a little bit differently. Oh, I don't have to do it even this way, right? So then for now, for x in nums, prefix dot append what should we call it? Oh yeah, max of prefix 1 and x, right? We want a prefix max, and then we can return prefix, and that's it. And then now we want prefix max is equal to get prefix max of nums, oops, and suffix max is equal to get, why do I make the same typo twice? I don't know. Get prefix max of nums reversed, and also this answer reversed, right? And then that's pretty much it. And then we can even write it in the way that we understand it, or at least I've been understanding it, which is to say, we just do it for j, right? And then now we have, we also have a best thing, of course. Best is equal to, I guess, negative infinity, because I think technically, it could be, because this could be 0, this could be, I guess this cannot be negative, right? I mean, it doesn't really matter because we can still keep it negative infinity. If we, like during a contest, if you have any doubts, just make it negative infinity instead of debating it. But now I'm curious about what the minimum value of this can be, right? So this is going to be at 1, this could be 2, but whatever this is, because this nums of k is going to be bigger than nums of j, right? So that means that if you rewrite this as something like this part is going to be positive. So then this is this number plus another positive number. So this is always going to be positive. So so you can actually even choose this as best as you go to 0, and that should be fine. And then now we go, okay. I don't. So okay, yeah. So then now the score is going to be equal to prefix max of j, keeping in mind that there's a 0 prefix here, so j should be the one that does not include the current index, minus nums of j plus suffix max of, I want to say j plus 1, but I could be off by 1 here. And then best is just max best of score. For science, we can type score. We could print out the score, but also what we want to do is also skip the first two and the last number because they are not valid choices, even though we would, because those are I and K's, right? So this one's gonna be 8. That's at least a good sign. That doesn't. Okay, so I'm clicking on use example cases, but it's just not coming up. I was wondering if I just missed something, but all right. So this is gonna be 2 and 4, huh? We put 2 and 8, which is no bueno. Did I mess up anything? Oh, I did. I messed up this problem, huh? I actually okay. I might have to revisit this. I rushed through this one because I missed. Oh, I didn't. I don't know if I misread it, but I missed it in my head for some reason, huh? Okay. I mean, I missed this condition, so that means that nums of I has to be less than nums of j. Okay. We might have to rewrite some stuff. I mean, there are a couple of ways we can do it. The suffix, I think, still makes sense, right? Because if we brute force on j, which we are kind of doing with this loop, if the suffix, I mean, all we have to do is do a check, because if suffix max is not bigger than nums, then there's no possible answer anyway. And this part, given this formula, we always want to maximize this because we always want to maximize this as well, but now we want to maximize this such that this number is smaller than this number, which we can handle, right? That's interesting. I mean, I did read it correctly, but for some reason I kind of I don't know, having one of those days where I just kind of forgot about it. But that's not so bad. What we can do then now is there are a couple of ways I can. I mean, there's already a easy way we can think about it. One is that just have a sorted list and then get the biggest number that we've seen before that is strictly smaller than nums of j. And that should be good. But I'm wondering if there is any O of n way of doing it. That's why I'm trying to think a little bit. I don't know. I think for now I'm just going to use the log n way, which for me is going to be used as sorted list. In other languages, it could be other, in other languages, it could be whatchamacallit. like order statistic trees or something like this, or just like a balanced binary search tree type thing, right? So if suffix max of j plus 1 is greater than num sub j, then we can do this. Well, and then we can do the thing. Huh. But yeah, I think the reason why I'm able to get this so quickly is because what we are trying to do is just break it into different components. Like I said, because we already focused on j, then on the right side we want to get the max that is bigger than j, which we already can get very quickly. But on the left we have this additional this constraint on the right is that the max number has to be num sub j, but because they're in the same direction, because you're already getting the max, and the max has to be bigger than this anyway, that's a easy condition. On the left, you want to get the biggest number that is less than this, which in a way is a separate problem, but that problem that we can solve, which is what we're doing now, which is with the sorted list. And yeah, basically this is saying that after we process j, then now we can add num sub j. This becomes I for the future, right? This actually should be inside the if loop. And then now we want to do a binary search on num sub j. So this is going to be the index that is the first number that is the same as the number that we're looking for. So index minus 1 is greater than 0, right? Then now we take index minus 1 is the biggest number that is smaller than this number. So we have this as the prefix max, I guess, in a way, but I don't know if that's still right. And then now score is equal to this thing. I think we're good now though. Except for typos. Sorted containers. Okay, that's a little bit unexpected. It just basically means that this has never happened. Do we go here? Hello. Okay, so we definitely. Oh, because then now because we skip. Well, now we don't have to skip the first number. The reason being that the first number, we have to add this to the first number. I mean, you could also skip it and then just add it manually, but this will make it better. There you go. But I think just to be a little bit cleaner, maybe if I could just add it to here, num sub 0. I think that's slightly cleaner than reading an implicit add. But yeah, let's give it a submit. Yeah, so this is going to be n log n dominating by the sorted list bisect left. I am wondering if there's a easier way to do this. I mean, I guess you can still do it linear time, because basically now this is n log n because of this, but I think you can reduce this by yeah, I mean there's a linear way. I'm gonna do it the linear way just because I'm a little bit annoyed at myself for misreading it. But you can see that this is n log n. But the way that to do it in the linear way is to kind of again deconstruct this problem, right? Basically, the way that we have right now is that we have to maximize this function, right? Let me delete everything. I don't. Yeah, I mean, let me delete everything and try over. It is another idea, another technique, maybe. I don't think it's a technique per se. It's just another idea that. But we're trying to maximize this function, right? And to maximize this, we can actually maximize this function first, and then we get. Let's define f of j is equal to num sub or negative num sub j plus num sub k, and of course, as we said, num sub k will be bigger than negative num sub j, right? So in that way, so then now we can maximize this. So this is positive, is what I mean to say. But then now we can produce this array for everything. And then now what we're saying. Wait, what am I saying? Am I right? Maybe I'm wrong on this one actually. I think I thought I had an idea about, because I think I was trying to reduce this to adding this to this, but I think that's not sufficient because that does not force that num sub j is bigger than num sub I. So maybe I'm wrong on this actually. Hang on. Well, I'm trying to think whether there's another way of doing linear time. So I'm curious whether there's a linear way of doing it. Just maxing over f sub j is not good enough. You have to max over the f of j such that num sub j is greater than num sub I. And I know that and there are ways to do it, but I don't think there's a linear way of doing it. I mean, or maybe, or if there is, it's just too hard for me to think right now. Because I think the idea. No, is that true? I think that if there's a way to do it, it's gonna be something like with a monostack. And I'm trying to think whether what I want to say is true. I don't think so. I don't think there's a, because basically the counter case that I have is something like 2 1,000, and then like 5 and 6 or something, right? If you have something like 4, 4 has to go with the 5 and 6. And the 2 would, in a greedy way, choose the 10,000, but the 4 cannot use the 4 to 10,000 because 4 is greater than 2. Right? So in that sense, if I was trying to do something funky, yeah, there's no like this idea of monotonicity that we can take advantage of with monostack. Let me cheat real quick. Let me take a look at hints. Okay. Alright, binary search. Alright, yes, okay, fine. And we did do all this stuff. But I'm wondering if there's a linear way. I guess not. No one else did it in a linear way. I was trying really hard to think about it though. I mean, this is not. Ooh, no, and sort. I guess after you sort it, maybe there's some funky things, but that's not O of n anymore, right? Like if you sort it and then you have the index C's, maybe you can do something funky, but that's already sorted. So okay, I'm wrong on this one, I think. Yeah, okay. Let me put up my solution back up then. Yeah, I guess that's all I have. I was wrong. I was trying to explore something, but I mean, that's fine. I think part of the up-solving sometimes is that you try to think about solutions, but then now it gives me the idea that, okay, we cannot really think about it that way. Okay. Sometimes you learn something in in general, you learn a lot more from failures, but if you're able to learn from your victories as well, that's also pretty good. So anyway, yeah, I think that's all I have. Oh man, I forgot to stand up for my watch. My watch always tells me to stand up, and I always forget. That's all I have for today, though. Thanks for watching. Yeah. Did I go over the complexity? No. This is linear space, and again, as we said, because of the binary search. So yeah, that's all I have for today. Thanks for watching. Stay good, stay healthy, to good mental health. I'll see y'all later and take care. Bye bye.